introduction, and I'm quite impressed how full it is here in the lecture hall. Yeah, that's great, thank you. For a Wednesday evening. So, in the next hour, I want to tell you something about the music of the spheres. And it's the link between astronomy and music. And to do so, I want to give you just a short motivation. Why should you be interested in the link of astronomy and music? And therefore, I have to give you some basics to understand the whole thing. So we start with basics in astronomy and physics. So, but don't be afraid. So there are no difficult equations or something like that. And in the third section, I will give you a short introduction into the music theory. So here called the Pythagorean scale, which is the basic scale for our musical system. And then the last 3 chapters are dedicated to the theories of astronomical harmony. Okay, so let's get started with the motivation. For the old Greeks and Romans, the music was not only playing instruments and singing, but the music was the embodiment of all harmonic dimensions. So, and there were 3 different kinds, and the first one is the one we know as music, or we usually interpret as music, so musica instrumentalis. So it's called the harmonic dimensions of music, of making music with instruments. The second kind is musica humana, so which says that there is harmony between the soul and the body, and harmony of soul and body. So it sounds a little bit like esoteric stuff, but I think we all can agree that if we hear nice music, then we feel good, right? Okay, so let's come to the most important part. This is the musica mundana, which says cosmic dimensions give us the music of the world. So this played a most important role in the medieval era and led to the worldview of the cosmology for the medieval era. So let's have a look at this system. So do we have a pointer or something here? It's not working great. Okay.
It needs to switch off.
Okay, yeah. So what we see here in the center is Earth. So a kind of picture impression here. And then we see on the first sphere that it's called Luna, so that's the moon. And then we see, followed by the fourth sphere, so it's called Solis, so this is the sun. And in between sun and moon, we see the Mercury and Venus, which are followed then after the sun by Mars, Jupiter, and Saturn. So this is basically the idea of the medieval people of the structure of our solar system. And it's followed by the so-called firmament, or the sphere of the fixed stars. So this was introduced by Plato, and afterwards we find the 9th sphere, which is quite a religious thing. So it's inferred from the Bible, from the Genesis, and this 9th sphere is the home of all the saints, and it's said to be the cause of the motions of all the inner spheres. And last but not least, there we have the 10th sphere. So this is home of God and all the angels, and called Empyrean. Okay, so now I gave you the idea of the old Romans and Greeks of the connection between music and astronomy. So there is no connection, but it's the same for them. So, and therefore, let's start now with some basics in astronomy. And here I have to introduce the typical problem for scientists and musicians. The musicians say, okay, come on guys, it's not rocket science, and the rocket scientists say the same about music theory. But we are happy to have people like him. So this is Brian May of the band Queen, and he has a doctoral degree in astrophysics, so he can explain music theory and astronomy. So let's use him to follow our next thing. So remember what I showed you here. So this is the medieval cosmology, and here we see a more schematic plot of the same system. So we see we have the geocentric system, geocentric because Earth is in the center. So it's a little bit like the politicians see the world now, right? So everything orbits around us. So, okay, great. We see, so we have the moon around Earth, we have then here Mercury and Venus, here's the sun, and then Mars, Jupiter, and Saturn. So if you miss some other bodies like Pluto or Uranus, they were not known in the old system. So it's just these 7 objects. But what we know is geocentric system, it's not working that way, right? So we have the sun in the center. And this so-called heliocentric system was introduced by Nicolaus Copernicus in the 16th century. And this is the world, how it should work for us, right? The sun is in the center, then we have Mercury, Venus. And then, interestingly, we have Earth. And the moon is not orbiting the sun, but the moon is orbiting Earth, right? And then we have Mars, Jupiter, and Saturn. Okay, so now you have an introduction to our solar system and impressions of how it works. And now let's come to a little bit of physics here. And let's start, no, that's not right. So we start with what is a star? Easy, because what's the difference of Earth and Sun? Exactly, we have to clarify that. So in here, we have to say, okay, a sun is a massive luminescent celestial body made of hot gas and plasma. Okay, so and there I just show you some objects. So what we see here, could the children perhaps imagine what is this called? Yeah?
That's a blue supergiant.
Great, that's right. So astronomers are not imaginative with the word, so it's blue, it's a giant, it's a blue giant, right? Okay, so then you can have the next one. This one here? It's a red giant, yeah, okay. So and then what we have here in yellow, this is our sun, and it looks very dwarf-like, right, compared to these ones. But do you see it here? There's a little red one as well. So, and this one is called a red dwarf. So as an example for that red dwarf, so we have here Wolf 359. Somebody did hear this word already? So yeah, so it's the place where the Borg attacked the Federation. Yeah. Okay, so now that we know what a star is, we have to know what's the difference to Earth. So what is Earth? Earth is a planet, and a planet is the celestial body which possesses an orbit around the sun. Okay, great. So all bodies orbiting the sun are, at first, perhaps a planet. But then they have to be of spherical shape as well. So Earth, fine, great. And then there is one important point, which is the dominant object on its orbit. So this means if this object does not tidy up behind, then it's not a planet. And this is the reason why Pluto is not a planet, because he can't tidy up his space. Okay, so children, please tidy up or you get punished by astronomers. Okay, so if you felt a little bit depressed by the size of our sun, I hope to increase this feeling a little bit by comparing the planetary size to our sun. So here you see this is Earth compared to the sun on the left side. So we are not even the largest body in our solar system. This is Jupiter, and even Jupiter is 1,000 times lighter than the sun. So just to get an impression, we are really small and unimportant in our universe. But okay. Now let's come to physics. We have to think of, so since I want to talk about music of the sphere, so we have to get to know some words which are music related. So then we have to ask the first question, what is a tone? And a tone is a simple vibration of a body. What is a vibration? Something like this. So please don't look too strong on this picture. I don't want to get you mesmerized, but it's just, okay, so if you have a pendulum just swinging in one direction and the other, this is a simple vibration. And then what a musician calls a tone is actually a sound. This is the sum of several tones. So if we speak of a piano tone or something like this, it's actually a sound because it's characteristic for this instrument and always the sum of several tones. A tone is something which you hear when you go to the ear specialist and try to get your hearing tested, right? Okay, so and then we have the noise, which is completely chaotic. It means though you don't have a pendulum, you just swing something wild without any rule behind it. Okay, so now as I said, vibration is a tone of an elastic body, but what is an elastic body now? So does somebody have an idea of elastic bodies? Yeah?
So an elastic body is something that can vibrate freely without on its
An example?
point. So like a guitar string.
That's good, yeah. Somebody else? Oh, come on. Okay, so yeah?
a body that if you distort it, then it reverts to its original position.
Yeah.
And it actually goes beyond it.
Yeah, so perhaps an example for elastic body. So we have strings already. So here, for example, for violins, guitar strings, and even pianos have strings. So perhaps something else what can vibrate. Yeah.
The reed from a wind instrument.
Yeah, that's good. Yeah, great. Yeah,
A toy.
a toy.
A toy has an elastic body.
That's right. Okay. Right.
Drumstick.
Yeah, that's good. Okay. So to get a little bit on with time, so you want to do stargazing again. So we have bars like xylophone or glockenspiel, and then we have the membranes of the drums, and then what we hear the wind bars for example, the wind in a pipe of a pipe organ. Okay, so now we know what is vibration, we know what is a tone. So let's come now to music theory. So, and then we start with the Pythagorean scale. And as the name says, it comes from our famous Pythagoras. And he did some very interesting experiments 2,500 years ago on the so-called monochord. You see it here. So it's basically a block of wood, which has, hopefully you can see it a little bit, so there are two strings fixed on it. And what he did is a kind of, so he compared two strings, he worked with one string. And since we have a lack of an instrument here, I will use the violin to improvise that. And the first thing is, he investigated the pitch of the tone. So, and the pitch of the tone is linked to the length of the string. So as you see here. So what is written here basically says that the shorter the string is, that the higher the pitch. So, and I think you can hear it. Yeah, okay, so the shorter the string, the higher the note, the higher the pitch of the note. Okay, so and then he did some quite funny things about harmony. So he compared the length of different strings with each other and found that there are some kind of ratios which are interesting. So, and he called that intervals. So intervals are the ratios between different tones. And what he did is then now, okay, he investigated different intervals. So let's try with the violin, different intervals. So perhaps somebody can hear what an interval it is. Okay, so it sounds not so strange. I tuned it before, okay. And then we have something like this. Okay, so there are special ratios of strings. We can even have something completely weird, which sounds really... Okay, so if you feel remembered on your last visit with the dentist, yeah, that's right. Okay, so but to go on, so he found by investigating that there are special ratios. So it's quite simple with that. It's 1 to 2, 2 to 3, 3 to 4, and 4 to 5, which he found. And before you get afraid of, oh God, there are so many numbers, and I don't know what she's talking about, I will show you this with the help of a piano keyboard. And hopefully everybody of you already saw a piano keyboard, right? So I don't have to explain. So we have black keys and we have white keys. And please ignore the black keys for the moment. So let's start with this one. This is the so-called octave, and it has a ratio of 1 to 2. Why is it called octave? So there are 8 white keys in between, and octave means 8, okay? So this is quite simple. So then you can tell me what the next one is. Great, it's a fifth, right? It's so easy. So, and this has a ratio of 2 to 3. So let's come to the next one. 4. Yeah, great. Okay, so I made it too simple for you, I see it. And then, of course, we have the last one. This is the third with a ratio of 4 to 5. Okay, so now the system is rather easy. And what the old Greeks try to do is they try to find the smallest step for each key. So to say, okay, start here, and then I get with the same step to each interval. But it didn't work. So because the distances between each keys are different, and so we had to wait until the well-tempered scale came, and this was really 2,000 years later, basically. And it was introduced by Andreas Werkmeister, and then, of course, used by Bach with his famous well-tempered organ. And the idea behind that is we can't just use simple ratios, we have to use logarithms and power laws to get the equal sized steps there, because our world functions in logarithms. Okay, so now let's come finally to early theories of astronomical harmony. So, and since it's early theories, please be reminded we have the geocentric system. So now everything orbits around us. And there we start with Plato, and there is his famous report on the creation of the world, and this was given by a figure in his report by Timaeus. And this Timaeus said that the creator came and made a sphere, because the sphere was the perfect shape. And this sphere got a motion around its center. This is the perfect motion. Of course, the creator does everything perfect. And then this creator took the square numbers and the cube numbers, or better, he invented the square and cube numbers, and then he created more spheres within this sphere. And then he used different materials and used this sequence here given to generate more material. And so it's quite esoteric stuff, so, but made a lot of fun to read it. So, and from this point of view, the Pythagoreans say, okay, this sequence of square numbers and cubic numbers is the most important thing to understand music theory and, of course, the structure of the world. For example, this great creator develops the harmonic and arithmetic mean. What does that mean? Okay. We have the numbers 1 and 2, for example, for the square numbers. And if we calculate the harmonic mean, it gives us a fourth. And if we use the arithmetic mean, then it's a fifth. Okay, so you might be suspicious, but yeah, it's connections. And what then Plato says is, okay, the creator formed our world. So we have the sphere, this outer sphere, and then we use these ratios to generate the inner spheres, which are obviously, in his opinion, the orbits of our known planets here. And he said, okay, we use the sequence to get the distances to Earth. So, and if we use this sequence, now ordered by number, we get, of course, an octave, a fifth, a fourth, an octave again. So what we see here is 2 to 1, 3 to 2, and so on. And if you write that down, you get something like this. So note there is a key change, a clef change here. And it sounds like a little bit weird. So yeah, you can do it, but you needn't. But I mean, it's music of the spheres who says that it has to be pleasing for the human ear. Okay, so, but this was the first theory of that. Another person came some 100, 100, 200 years later, the so-called Nicomachus, and he said, okay, our Greek lyre has 7 strings, and we have 7 known planets. That's no coincidence, obviously. Okay, so a Greek lyre looks like this, and yeah, the more modern version looks like this. Okay, but what they said, okay, each string resembles a planet, and they said, okay, Saturn is the farthest planet in our system, so the farthest string sitting here is Saturn, and the closest one is the Moon, and in the center we have Sun, so something like here. So we get a scale, a so-called planetary scale. So, and you can just write that down. And this looks nice, looks easy. For musicians, if you wonder why there is a B flat, it's a shared 2 tetrachord in A, and it's a hypophrygian note. Okay, so just accept that. Smile, nod. Okay, so but this was a second approach in the early science of astronomy and harmony. And now let's do a kind of a time slip to Kepler. So we now go 2,000 years in the future. and start with Kepler. Now we change the system. We are not geocentric anymore, we are heliocentric, so Sun in the center and Moon orbiting Earth and so on. And Kepler's first idea was to say, okay, our planets move through something like air, and therefore they have to make some sounds, like the strings of an instrument. And these sounds are influenced by the speed of the planets, and he inferred the speed of the planets on their orbits from polyhedral theory. Okay, yeah, you look as excited as I am. Polyhedral theory, what is that then? Okay, something like this. So he said the polyhedra can describe the distances between the planets. And what we see here is, for example, the sphere of Saturn. And the next sphere here is the sphere of Jupiter. And in between we see this cube. A cube is a polyhedra. And he said, okay, so if I can fill in a polyhedra with certain size lengths here to describe the distance. And if we go further in, we see a tetrahedra, and we octahedra, and dodecahedra, and so on. So trust me, it's not getting easier. And he just says, okay, I can infer the distances of the planets by these polyhedra, and therefore I can infer the speeds of them. And if I use that, I get something like this. So I get the speed, and if I compare the speed to the planets, I get something like a fourth, an octave, a major third, a minor third, a fourth. And it looks like, if you combine that, something like this. This looks nice, and it sounds nice, right? So much better than the first. But it's just his first theory, because he knows, okay, polyhedra theory is kind of weird and just an approximation, and there must be other laws in it. So what he did is 30 to 40 years really research in harmonies in the solar system, and before he wrote his famous World Harmonic book. And then, but what he found in between are his famous Kepler's laws. So there are three Kepler's laws, and we start with the first one, obviously. So the first one just says, okay, a planet moves around the sun on an ellipse, while the sun is in one of the foci of the ellipse. This is nice, this is easy. So it's not a circle, it's an ellipse. And then he has a second law. So it's called the area law. It just says, okay, a line going from the sun to one of the planets, and they're sweeping an area. It's the same area always if the planet is measured for the same time span. So this means if the planet is close to the sun, it's faster than it's far away from the sun. So it's a little bit like school. If the teacher comes closer, you're faster working your task, right? So just, it's exactly the way. So you have the same area here, and because of that, the planet's faster. Okay, so and then he has his third law, and it's even called the harmonic law. That's nice, right? To say, okay, it sounds rather mathematical, but I will explain it to you. So the squares of the orbital periods of two planets act like the cubes of the semi-major axis of their orbits. That's nice, right? So every 15-year-old before an exam. That's great. Okay. So this means just we have one planet orbiting in a time t1, and we have a second planet, which is, for example, far out here, and it has a time t2. And the distance of the planets to the sun are given by A1 and A2. And this basically just means we follow this law here. And it means that a planet closer to the sun is faster than a planet further away from the sun. Okay, this is nice. So now we have the three Kepler's laws. And now Kepler was asking, okay, where should we look for harmonies in our solar system? And he said, okay, we can take the distances from the sun. So we started this with the polyhedra theory. And then we go on planets, periodic time, planets true daily path, okay, planets angular motion. This basically means speed. But okay, so he started with the distance from the sun. And therefore, we just have to do a little bit of work here. So we have here an ellipse. We have the sun in one of the foci. And then we have the planet's position closest to the sun, so-called perihelion. So helion from sun, this is, I think, Greek. And then we have the aphelion, so this is the farthest position from the sun. So and then he introduced a second planet because we always compare planets to each other because we are talking of intervals. And then he said two extreme cases. We have one planet, the inner one is farthest away from the sun, the outer one is closest to the sun, and then we just change positions. Then we have the inner planet closest to the sun. And then we compare the distances. And now comes the most important part in this thing. What he really found, 9 out of 10 of these positions show harmonies. So it's not 3 or 4, it's really 9 out of 10. Except Earth and Venus, so obviously we don't like Venus, it's okay. It's octave, major 6, double octave, so really you can really make music out of that. So our solar system is a really musical one. That's nice. If you want to know why these are printed in blue, so Kepler didn't say that here are harmonies, but if you compare these values, for example, to the 3 to 4 for a fourth, then you see this is really close. This is just a difference of 0.00, I won't go on, but it's really close to fourth. Okay, then we check actually the speed, so what I showed you earlier, so he followed this idea to show the speed. And what he did is he said at the aphelion we have a certain tone for the planet, and in the perihelion we have another tone. And he put that into notes, and now every planet gets a scale. So here we see Mercury going from an A up to a C here. And then we see Venus and we see Earth and something like that. So you can really make planetary music out of that. But some people see that as his summary of the world harmonic. But here he just wants to say we have every ecclesiastical scale here in the planetary scale. So all our music theory goes into this. More he doesn't want to say. Okay, so now coming to close to the end. So a fun fact is he was also looking at planetary periods to say, okay, we compare how long is a year for Earth, how long is a year for Mars, and he said he didn't find any. But this is quite ironic because modern astronomers are now looking for these kind of periods because we have them in our solar system. For example, if we look here, these are the Galilean moons of Jupiter. So, and they actually have these resonances which Kepler didn't see. And for example, so he didn't know the planets Neptune and Pluto. Pluto is not a planet, okay? But these two planets have even a resonance between of 3 to 2. So this means they are actually in a fifth to each other. So now, summing that up, so I want to relax you a little bit now. So after this whole weird stuff a little bit, there were some astronomers which had too much time and summarized the whole planetary stuff, which Kepler did, for another planetary system. It's a famous system which was found 2 years ago. It's called TRAPPIST-1. And here they found 7 planets around another star. And if you sum the whole music of the spheres up, you get something like this. So hopefully it's not enough. Astronomers and musicians, and perhaps you can say who it is. Silence. Okay, that's nice. Friedrich Herschel So he is the, he found that in our system we have Uranus, and he found even the infrared radiation. So this is the famous one. So his son was even one of your higher Royal Society thing stuff. Don't know. So, but yeah. Okay. So it's Herschel. Okay. Next one. It's a woman. Okay. This is difficult. So it's his sister. Caroline was a concert singer, and she was famous for the discovery of several comets. And she was corresponding with the Royal Astronomical Society and such stuff. But obviously nobody gets told that, yeah? The next one, there are 3 reasons why I put her here. First reason is obvious, she is a girl, okay? Yeah, she would probably don't know now. This is Charlotte. She was a princess in Germany, and she was a composer because all princesses were music people. And she was as well an astronomer, very acquainted with Gauss, for example. And she was what we call today a computer. So she generated the tables which were used by the astronomers for stellar positions and something like that. And okay, the third point is she comes from my home kingdom. It's okay. Okay, the next one you know. Yes, that's right. I hear from here. So he composed, obviously, the Jupiter Symphony. So even just a musician can do some astronomy. So even if it's just Jupiter. The next one. Yeah. Okay. This is Gustav Holst. Okay. Yeah. He composed the famous planet. And now the next one.
Biggie T?
No. Composed this. Okay, so this is Alexander Courage. And of course, okay, so now last but not least, I show you the last slide. And this will be a nice video. It's another way of showing astronomy and music. So last month we got a Nobel Prize for exoplanets, and our team here so we have a colleague who got it, actually. And he was the discoverer of the first exoplanet around the solar type star. And this star is called 51 Pegasi. So, and I hope you enjoyed this video. And with that, I close the talk so far. So,
was a world by the North Pole star, that's true, but the news is a sun-like star with baubles of quick and precise to be known.